All right, today we are going to revisit sign analysis. And so we have done sign analysis with quadratics. Now we're going to do it with our higher degree polynomials. And so sign analysis uses a number line to model the x-axis. And then plus or minus signs to indicate where the function is positive or negative. And so if the question says use sign analysis, you need to have a number line and plus or minus signs to show that you're doing that. And then we're going to be writing our solutions in interval notation. So that's the parentheses and brackets. Okay, so your first step is to factor each of these. So we're going to get a review of factoring. And so anytime you have an even number of terms, always try to factor by grouping first. So out of this first pair, I can factor out x squared, which leaves x minus 5. Out of the second pair, I can factor out a negative 4, which also leaves an x minus 5. And so factor by grouping is going to work. X minus 5 is one of my factors. X squared minus 4 is the other factor. And then we're not done because x squared minus 4 is a difference of squares. That would factor to x minus 2, x plus 2. And so when you're factoring a degree 3 polynomial, your goal is to get 3 linear factors. And in this case, that's what we have. And so this is the completely factored form. So I'm going to highlight that just because that's what we're going to be using to do our point testing. It's going to be easier to use the factored form. And then I'm going to bring back my inequality. We'll need that to determine our final answer. And so after you have your factors, you can find your roots or your x-intercepts. The first factor is x equals 5. The first factor leads to x equals 2. And then the last factor leads to x equals negative 2. And so you're going to put each of those on your number line. And because our inequality has an equal to sign, we're going to use closed circles. If that equal to option wasn't there, we would use open circles. And so these closed circles. And so make sure you put them in order. Negative 2 would be on the far left. And then we would have positive 2. And then positive 5. And so we're going to pick a test point in each interval. And so negative 3 would be a good test point to the left. 0 would be a good test point in the middle. 3 would be a good test point between 2 and 5. And then we could test 6 to the right of 5. So 4 test points for each of our 4 intervals. And so I like to just get the setup. We're plugging in x equals negative 3, x equals 0, x equals 3, and then x equals 6. And so these will not end up in your final solution. These are just test points. So be careful not to mistake those as your critical values. And so we're going to plug these points into each of our 3 factors. And so I like to put 3 sets of parentheses just to get the setup. Now, if I plug in negative 3 into my first factor, negative 3 minus 5 is negative 8. So that's negative. Into my second factor, negative 3 minus 2 is negative 5. So still negative. And then negative 3 plus 2 is negative 1. So still negative. Negative times negative is positive, but times another negative would result in a negative product. So this interval over here would have a big minus sign. If I plug in 0 to each of the 3 factors, I would get negative 5, negative 2, positive 2. And so that result would end up being positive. If I plug in 3, I would get negative 2, and then positive 1, and then positive 5. So this result would be negative. And then if I plug in 6, I would get positive 1, positive 4, and then positive 8. So this result would be positive. Okay, and so this has a nice pattern, negative, positive, negative, positive. Because if you remember from graphing these polynomials, each of these x-intercepts have a multiplicity of 1, and so each one would just be a cross. We would cross through the x-axis each time. And so we go from negative cross to positive, and then nothing weird is happening. And so that's why we have that nice pattern. But remember, polynomials, sometimes they bounce, sometimes they twist, so it's not always this nice, even pattern like that. And so for our solution set, we're looking for where it is greater than or equal to 0. And so we're looking for our plus signs. And so we have two plus signs, one between -2 and 2, and the other beyond the 5. And so when we write our solution set, we're going to have to use a union and brackets because these are closed circles. And so from -2 to +2 bracket, union, pick back up at 5 and go to infinity. And so a couple mistakes I saw in Unit 5 is accidentally putting the test points. And so make sure you're actually using your critical values for your solution set, not these test points written in blue. Okay, for this next example, we need to set everything to 0. So the first thing I'm going to do is move this 12x cubed to the other side. And we're going to put it right between the x4 and the x2. And so we get 3x4 minus 12x cubed plus 12x squared less than 0. And so right off the bat, I'm noticing I can divide everything by 3x squared. That's our GCF. And so we're going to go ahead and factor that out, leaving me with x squared minus 4x plus 4. And that's a perfect square trinomial that factors to x minus 2, x minus 2. So I'm going to write that as x minus 2 squared. Now this is the completely factored form, so I'm going to highlight it and then bring back the inequality. And so for our x-intercepts, we would get x equals 0 from the first, and then we would get x equals 2 from the second factor. And both of these have a multiplicity of 2. And so this is a degree 4 polynomial with only 2 x-intercepts. And from our graphing polynomials lesson, we know that the polynomial is going to bounce at each of these x-intercepts. And so when I graph them, I'm going to use open circles because there's no equality option. And so an open circle for the 0 and then an open circle for the 2. And then for picking test points, you could choose -1, +1, and then +3. But if you look at our factors, everywhere I plug in an x, so for example, if I plug in -1, I'm going to square it, it'll become positive. If I plug in -1 here, I would get -3, but then we square it and it's going to become positive. So no matter what you plug into these factors, they're always going to be positive times a positive. And so this entire function is going to be positive. And so when we're looking at our inequality, we want to know where it is strictly less than 0. Well, this polynomial is never going to be strictly less than 0. There's no minus signs. And so our solution for this would be no solution. It's never negative. But I want to look at if we had a different inequality here. If instead of less than 0, I had less than or equal to 0, we would have exactly 2 numbers in our solution set. We would have the x-intercepts because that's where it's equal to 0. And so we wouldn't even have an interval of numbers. We would just have a set, 0 and 2. That would be it. If I change the inequality to strictly greater than 0, we would have 3 intervals to point out. We would have the part less than 0, the part between 0 and 2, and then the part greater than 2. All 3 of those intervals are strictly greater than 0. And so we would say -infinity to 0, pick back up at 0, go to 2, pick back up at 2, and go on to infinity. And then lastly, if it said greater than or equal to 0, we wouldn't even have to skip over these x-intercepts. The entire graph is greater than or equal to 0. So it would just be all real numbers or negative infinity to infinity. So just by changing that one inequality sign, it completely changes what your solutions would look like. You would either have no solution, you would have two distinct numbers, you would have three intervals, or you would have all real numbers. So you really have to think about what your inequality is asking you. All right, for this third example, we need to move everything to one side of the inequality. I'm going to move everything to the x to the fourth side just so my leading term stays positive. And whenever you're working with inequalities, you really want your polynomial to be on the left side compared to 0, just so you don't get confused with that less than or equal to sign. And so the inequality should still be facing the polynomial when I rewrite it. And so now we can more accurately read what it's saying. And so to factor this, I'm noticing that I have a trinomial that goes from x4 to x2. And so if I let u equal that x squared term, I could rewrite this as a quadratic, u squared minus u minus 40. And then we can factor this if we find two numbers that multiply to negative 40 but add to negative 6. That's negative 10 and positive 4. So this factors to u minus 10, u plus 4. And so I can bring the x squared back. And then as I try to factor this further, x squared plus 4, those are perfect squares, but we can't factor it as a difference of squares if it's a plus sign. So that's prime. And then this 10 is not a perfect square, so this is also prime. And so this is the best we can do as far as being completely factored. So I'm going to go ahead and highlight that. We'll use it for our point testing, and then bring back my inequality. And so to solve for our x-intercepts, we can use our square root property. X squared would equal positive 10, and so then x would equal positive negative square root of 10. Over here, x squared would equal negative 4, and so x would equal positive negative 2i. And so these are imaginary, so these are not going to show up on our x-axis. The square root of 10 is real, it's just irrational, but those will show up on your x-axis. So those are the only two x-intercepts we're going to be able to graph, even though this is a degree 4 polynomial. And so when we graph them, we're going to use closed circles because we have the equality option. And so one closed circle at negative square root of 10, and then the other at positive square root of 10. And so when we're picking test points, 0 would obviously be a good point between them. And then square root of 10 is less than square root of 16. And so 4 would be a good test point here, and negative 4 would be a good test point out here. And so 3 intervals to test using negative 4, 0, and positive 4. And we're plugging them into two different factors. So I'm going to put 2 sets of parentheses for each case. And so if I plug in negative 4 squared is 16, minus 10 is 6, so positive, and then 16 plus 4 will be positive. And so that same result's going to happen if I plug in positive 4, 16 minus 10, 16 plus 4. And then if I plug in 0, I'm going to get negative 10 for the first factor and then positive 4 for the second. So that ends up being negative. And so we have a plus, negative, plus. And if you're trying to picture what this degree 4 polynomial looks like with those imaginary roots, it's above the x-axis, and then it's still twisting and turning. It just doesn't cross the x-axis between the roots. It just does it below the x-axis. And so to answer the question, it wants to know where is the polynomial greater than or equal to 0. So those are our plus signs. And so one interval is less than or equal to the negative square root of 10, and the other is greater than or equal to positive. And then we're going to use brackets because those are closed circles. Okay, for our last example, we're going to talk about what to do if you can't factor by grouping. And so the first thing you're going to want to do is factor out a negative x, because that would be a GCF. And that would leave 4x cubed plus 16x squared plus 5x minus 25. And then you don't want to flip the inequality because we didn't divide by the negative and get rid of it. We just factored it out of the left side. You only flip your inequality if you're dividing both sides by, say, a -1 and then getting rid of it. And so now this cubic looks like we should be able to factor by grouping, but I would be left with an x plus 4 on this side, and I would be left with an x minus 5 on this side. And so this one actually isn't factorable by grouping. And so this is one of those cases where we have to just guess and check different roots. And so I always start with positive and -1. And so just focusing on this cubic, I'm going to test and see if +1 is a root. And so using the coefficients 4, 16, 5, and -25, bring down the 4, multiply, add, multiply, add, multiply, add, and we get a remainder of 0. So that means 1 is a root. And so that means x minus 1 is the factor. So I'm going to go ahead and write down that factor before I forget. And then remember, you always drop the degree by 1 when you're using this synthetic division. And so that means this is my 4x squared term. And so I have 4x squared plus 20x plus 25 as my remaining factor. And that's a perfect square trinomial. If I square root the first term, I get 2x. Square root the last term, you get 5. Copy the sign of the middle. And then always check. 2x times 5 is 10x. And this middle term is twice as much. So this works. And so put parentheses around it and make sure you square it because it's 2x plus 5, 2x plus 5. And so that's our final factored form. Don't forget the square because we have a degree 4 polynomial. And so I'm going to highlight that. We're going to use it for our point testing. And then bring back the inequality greater than 0. Okay, so our x-intercepts, we have x equals 0, x equals 1, and then x equals -5/2. And then remembering from our graphing polynomials lesson, we know it's going to cross at these two x-intercepts, but it's going to bounce at this x-intercept. And so we'll see how that plays into the signs. And so we're going to put these on the graph, and we're going to use open circles because we don't have the equality option. And so make sure you go in order. The -5/2 would go here, followed by the 0, followed by the 1. And so as we're picking test points, -5/2 is -2.5. And so you could use -3 for the left interval. You could use -1. And then for 0 and 1, there's not an integer between those. And so you have to use a fraction. But you don't have to simplify all the way. You just need to know if it's positive or negative. And then we could use 2 for the final interval. And so 3 intervals to test, or 4 intervals to test, using -3, -1, 1/2, and 2. And so we're going to plug these into 1, 2, 3 different factors. So I'm going to put 3 sets of parentheses. And you have to be really careful with this negative x. And then something else you might notice is this factor is being squared. Anytime you're raising a factor to an even power, whether it be squared or fourth or even to the sixth, it's always going to be positive. If it's cubed, it's not always going to be positive. It's only when it's an even power. And so because we have an even power for that last factor, you can go ahead and put in your plus signs for that last set of parentheses, because that factor will always lead to a positive regardless of what we put in for x. Okay, and so now plugging in the -3, I would get -3, which is positive. And then for the x minus 1, I would get -4. And so positive, negative, positive would result in a negative. Plugging in the -1, I would get -1, which is positive, -2, which is negative. So this result would also be negative. And so my first two intervals are negative, negative, and that makes sense because that's where our bounce would be. And so this polynomial would go up to the x-axis and then bounce right off of it and then head back for the 0. If I plug in 1/2, I would get -1/2 and then negative and then positive. So this would result in positive. So this one's going to cross. And then plugging in the 2, I would get -2, +1, and so this result would be negative. And so you can see the quadratic or the polynomials going back down and stays negative. And so to see what this question is asking for, they want to know where it is greater than 0. So we're looking for our plus signs, and that is only the interval between 0 and 1. And so because we have open circles, we're going to use parentheses and just say 0 to 1. But again, if I change that inequality to greater than, or if I change it to less than 0, I would have 3 different intervals to report. I would have -infinity to the -5/2. And then I would pick back up after the -5/2 and go to 0. And then we would pick back up at 1 and go to infinity. So skipping over those x-intercepts because we have open circles. If instead I had greater than or equal to 0, we wouldn't even have to skip over the x-intercepts. We would just go right through it. And so our interval would end up being -infinity all the way to 0, and we would use a bracket and then pick back up from the 1 and go to infinity. So be very careful with these inequalities. Changing one small part of the symbol completely changes what your solution looks like.